Good evening, dear students. Today I will explain the working and designing of a special amplifier known as instrumentational amplifier. A instrumentational amplifier is a type of differential amplifier with input buffer amplifier. Many industrial and consumer application requires measurement and control of some physical conditions such as measurement of temperature and humidity inside a dairy plant to accurately maintain product quality or precise control of temperature of a plastic furnace to produce a particular grade of plastic. So, instrumentational amplifier is mainly used in industry where we want to control some physical conditions such as measurement of temperature, humidity, and pressure, etc. These physical changes in must be converted to electrical quantities using transducers, and then it must be amplified. Such amplifiers, which are used to amplify signals to measure physical quantities, are commonly known as instrumentational amplifier. The input to an instrumentational amplifier is the output signal from the transducer. A transducer is a device which converts one form of energy into another. Most of the transistor output are of very low level signal. So these low level signals must be amplified before it converted into a electrical signal, and the amplifier used to amplify these signals are known as instrumentational amplifier. Hence, before the next stage, it is necessary to amplify the level of the signal, rejecting noise and interference. The general signal-ended amplifiers are not stable for such operations. Therefore, for rejection of noise, amplifier must have high common mode rejection ratio. That is, it must have high CMRR. The special amplifier which is used for such low level amplification with high common mode rejection ratio, high input impedance to avoid loading is an instrumentational amplifier. Therefore, we can define the instrumentational amplifier for a precise low-level signal amplification where it must have high input resistance, low noise, and accurate closed loop gain. One of the other property which must have is low power consumptions, high slew rate, and high common mode rejection ratio are required for good performance. Now I will discuss some of the requirement of a good instrumentational amplifier. Instrumentational amplifier is usually employed to amplify low-level signals, rejecting noise, and interference signals. Therefore, a good amplifier, that is instrumentational amplifier, must have the following specifications. Number one, it must have finite, accurate, and stable gain. Since instrumentational amplifiers, they are required to amplify low-level signals from the transducer device, high and finite gain is the basic requirement. The gain also need to be accurate and closed loop gain must be stable. Second, easier gain adjustment. Apart from a finite and a stable gain, variation in factor or a precise range of values is also necessary. The gain adjustment must be easier and precise. Means we must have some mechanism to control the gain and adjust according to the requirement of the environment. Next important condition that must be specified by instrumentational amplifier is high input impedance. The high input impedance is required just to avoid the loading of input sources. The other condition is low output impedance. The output impedance of a good instrumentational amplifier must be very low. Ideally, it must be zero to avoid the loading effect on the immediate next stage. The other condition is high common mode rejection ratio and high slew rate. The slew rate of instrumentational amplifier must be as high as possible to provide maximum undistorted output voltage signal. Means the slew rate must be infinity, although we don't have the instrumentational amplifier which must have infinite slew rate, but it must be very high. The most commonly used instrumentational amplifier consists of three operational amplifiers. In this circuit, a non-inverting amplifier is connected to each input of a difference amplifier. This instrumentational amplifier provides high input impedance for exact measurement of input data which is received from the transducers. The circuit diagram of an instrumentational amplifier using 3 op-amp is shown in figure. Here, this is the input stage. This is the output stage of a instrumentational amplifier. The op-amp 1 and op-amp 2, they are the non-inverting amplifier because we are applying the input signal at non-inverting terminal of the operational amplifier. Here V1 is applied to the positive terminal, that is non-inverting terminal of the operational amplifier 1, and V2 is the input signal applied at the non-inverting terminal of the op-amp 2. This op-amp 1 and op-amp 2, which are placed in non-inverting configuration, are together form an input stage of the instrumentational amplifier. Op-amp 3, that is this one, is nothing but it is a difference amplifier that forms the output stage of the instrumentational amplifier. The output is obtained at the output terminal of the op-amp 3. Now, working of instrumentational amplifier. The output stage of a the output stage of a instrumentational amplifier is a difference amplifier whose output V out is amplified difference of input signals applied to the input terminals. Here in this case we are applying V1 and V2 at the input stage of the instrumentational amplifier. If the output of the operational amplifier V1 and V2, sorry, if the output of op-amp 1 and op-amp 2 are V01 and V02 respectively, then the output of difference amplifier, it is given by R3 upon R2 into the difference of output of op-amp 1 minus output of op-amp 2. The expression for V01 and V02 can be found in terms of input voltages and resistances. Consider the input stage of a instrumentational amplifier as shown in figure. This is op-amp 1 where we have applied V1 at the in non-inverting terminals. This is the feedback resistor RF, that is represented by R1 for sake of simplicity. This is the variable resistance R gain. Again, this is the R1, which is the feedback resistor for op-amp 2. The potential at node A is the input voltage V1, hence the potential at node V2 V. The potential at node B is also V1 from the concept of virtual ground. Thus, the potential at node G is also V1. Similarly, the potential at node D is V2, hence the potential at node C is also V2, which is again due to virtual ground. Thus, the potential at node H is V2. Now we can say the potential at G is V1 and potential at node H is V2. Ideally, the current to the input stage operational amplifier is zero. Therefore, the current through the resistor R1, R gain and R1 remain the same. Now we will apply Ohm's law between the node E and F, that is E and F. We apply Ohm's law. Applying Ohm's law at node E and F, we obtained I is equal to V01 minus V02 divided by R1 plus R gain plus R1. Or we can simply say that I is equal to V01 minus V02 divided by twice R1 plus R gain. Since no current is flowing to the input of op-amp 1 and 2, hence the whole current I between the node G and H can be given as I is equal to Vg minus Vh divided by R gain, or we can say V1 minus V2 divided by R gain. As the current is same at the input and output stage, therefore, equating equation 1 and 2, we obtained V01 minus V02 is equal to twice R1 plus R gain into V1 minus V2 divided by R gain. The output of a difference amplifier is given as V out is equal to R3 divided by R2 V naught 1 minus V naught 2. Therefore, V naught minus 1 minus V naught 2 is equal to R2 divided by R3 into V out. Now we will substitute the value of V naught 1 and V naught 2 in equation 3, and we will receive V out is equal to R3 divided by R2 into twice R1 plus R gain divided by R gain into V1 minus V2. Therefore, from the above equation, it gives the output voltage of an instrumentational amplifier. The overall gain of the amplifier is given by this term, that is R3 divided by R2 into twice R1 plus R gain divided by R gain. The point that must be noted is that the overall gain of an instrumentational amplifier is controlled or adjusted by R gain from the equation this. The common mode signal attenuation for instrumentational amplifier is provided by the difference amplifier, which is the output stage of a instrumentational amplifier. The gain of some of the advantages using 3 op-amp instrumentational amplifier are: number 1, the gain can be varied easily and controlled by adjusting the value of R gain without changing the circuit structure. The gain of the amplifier depends only on the external resistor R gain. Hence, it is easy to set the gain accurately by choosing the resistor value carefully. The input impedance is dependent on non-inverting amplifier circuit in the input. The input impedance of a non-inverting amplifier is always very high. The output impedance is the output impedance of a difference amplifier, and the output impedance of a difference amplifier is always very low. The common mode rejection ratio of op-amp 3 is very high, and almost all the common mode signals they can be rejected. Hence, in this lecture, we have discussed about the instrumentational amplifier. In the next lecture, we will discuss about the another topic, or we can say another application of operational amplifier. Till then, thank you a lot.